On May 29, 2023, the first ever indigenous atomic clock was launched on board the NVS-01 navigation satellite by the Indian Space Research Organization. And today, we are in conversation with the man behind this mark. Welcome to a brand new episode from the fifth season of Zirangin, the Science Podcast. Today, we are in conversation with Professor Thejesh Bandi, who is a prominent figure in the field of physics, specializing in spectroscopic studies and the development of precise instruments, particularly clocks. These clocks aren't just any timekeepers, they are the driving force behind the cutting edge satellite navigation systems like GPS, Galileo, and more. During his master's studies in the charming city of Cork, Ireland, our guest delved deep into rubidium spectroscopy and cold atom detection schemes. His curiosity led him to pursue a PhD in Switzerland, where he played a pivotal role in the creation of next generation clocks for the European Space Agency's Galileo navigation system. Professor Bundy's scientific exploration continued at the Jet Propulsion Laboratory, NASA Caltech. His work significantly contributed to the development of the Deep Space Atomic Clock, a remarkable feat that adds precision to deep space missions. Taking his expertise to the new heights, our guest assumed a leadership position at the Space Application Center, ISRO, where he spearheaded the development of indigenous clocks for the navigation with Indian constellation, Navik. His dedication led to the establishment of a clock cleanroom laboratory and the remarkable achievements of designing, assembling, and testing an indigenous rubidium clock in just 6 years. The Indian indigenous atomic clock's performance rivals that of the world's most finest space navigation systems. Joining the University of Alabama as an associate professor, our guest continues his passion for education, aiming to inspire young minds to explore the wonders of our world. With over 16 years of experience in building clocks, conducting spectroscopy research, and diving into meteorological studies, our guest's Precise Navigation Time and Frequency Lab promises to be a hub of innovation, collaboration, and learning. So fasten your seatbelts as we embark on a journey of precision science, technological advances, and the captivating story of Professor Bundy's dedication to understanding our universe and shaping the future. This episode is hosted by Sahil Mittal, Aditya Krishnan, and Rashi Jain. Join us in our conversation with Professor Bundy as we discuss at length the fundamental principles exploited to develop such accurate atomic clocks, while also detailing the advanced scientific research going on at the frontier of this field.
We usually ask this to all our guests, that what made you interested in this field specifically? Was it something your professor told you one day, or something that you saw that this is what I wanted to do in your undergrad, in your master's? So what was it that made you think of it in atomic clocks or time in general?
So, to answer your question, mostly I'm interested in physics. And the fascination when I was a young kid to look up the sky and then see all those stars and then wonder, are we alone in this universe? Is there life beyond that? And what are those stars and how far they are? To be able to identify the constellations, that has been kind of a fascination for me. And even today, I do that on a clear night. So that's kind of the motivation, and in which I could have gone towards engineering. I had an opportunity to go and get the engineering degree, but I wanted to stick with physics and then pursue my studies in physics. But I must say that at a later stage, I found out there is not much of a difference between engineering and physics if you want to do an applied physics. So when I was doing my master's in Ireland, that's when I found out that I need to do something more applied, which should be useful to the everyday life or mankind. But at the same time, I didn't want it to live far away from my physics world, and that's where the fascination towards atomic clocks developed. In the sense, there is core physics, that is atomic physics, and there is cutting edge electronics and spectroscopy, all that is involved in atomic clocks. So therefore it's a perfect bridge or amalgamation between physics and engineering. That's what kind of fascinated me towards atomic clocks, and therefore I do a lot of engineering as well as I do a lot of physics now, so that keeps me going.
Yeah, definitely, one can't have single thing without the other one. They are complementary to each other. Since you were mentioning a lot of fascination for physics in general, and you have been working with the concept of time for a long time, even not if like from the physics perspective, very engineering applied physics perspective, this might sound a little philosophical. But let's say if someone from your regular day life comes up to you and asks, "Can you explain time to me? What it is? Like, how do we make sense out of it?" Because it's a question that everyone thinks about it at certain point of their life, that what's time, what's moving. So can you give certain light on that? Yeah.
Yeah, that's one of the basic questions that we need to answer, right? Because anything that we look around in the universe, it's space and time. So then comes the question, space is something that you can clearly see and obviously feel it and you can touch, there are objects. But time is something that is elusive, but it exists, right? So Einstein, as he put across, time is relative. Depending upon how fast you're traveling, the time literally changes for you. Either it slows down or it speeds up. But obviously one cannot travel faster than the speed of light, and that's kind of the limit that sets for the time as well. So the speed of light, in other words, is a consequence of time, if you think of it that way. Okay. And whenever we say time, we look at our wristwatches and then say, this is what our time is. So, although we talk about time as a particular instant, what we end up measuring is the series of repeated events. For example, a day can be split into morning, afternoon, evening, and then night, right? So this is how we could kind of make four parts, but obviously they are not equal parts. Night is pretty long compared to this. So this is how, like 3,000 years ago in Stonehenge, that's why we have those structures of Stonehenge in which the shadow, was looked into, and then they were able to find out, okay, this is morning, this is afternoon when there is very little shadow, and then this is evening when the shadow is on the other side. So the idea is to be able to measure these series of events. In that sense, if you think of a pendulum, the tick of a pendulum, that's basically like 1 hertz, right? It has that swing of 1 hertz. Similar to that, when you look at the oscillations, there are series of natural oscillations. If we take of atoms, for example, they also oscillate between the two transitions. So the idea of being able to measure these oscillations, one can determine and then say what time it is. So that's how we always measure these cyclic events and then talk about, past, present, and future as a time. So this is the overall concept of time as we understand today.
So, could you elaborate some more on how do we relate time to an atom? Like, how would one visualize that? Literature suggests something called as hyperfine structures within an atom. What are those and how do they work? Could you throw some light on that?
Yeah. So, as I mentioned, the oscillations, whenever we talk of oscillations, we mean frequency. The number of oscillations per second is basically the frequency, right? Now, when it comes to the atomic structure, an atom has nucleus and the electronic states around the nucleus. The electrons are around the nucleus. Now, given this, the electrons can have different transitional orbits. Now, if that is the case, let's take, for example, the simplest of the atom, hydrogen. Okay. We do make atomic clock using hydrogen as well, which is called as hydrogen maser. Just like the laser, We have maser, which is microwave amplification by stimulated emission of radiation. Now, the way it works is hydrogen is the simplest of the atom, in which there is a single electron orbiting the fixed nuclei, right? Which means that this electron can have two spin states, either spin up or spin down. This is a quantum property. Now, depending upon what sort of a spin that you have, that will tell how much is the energy of that particular transition. If it is spin up, it has a certain energy, spin down, it has a certain energy. That means you can measure this energy difference. So that's where we talk about the hyperfine structure, right? Now, the hyperfine structure itself, that's an interaction between the nuclei and the electron. So this gives rise to the hyperfine structure in any atom. And in that particular property, what we measure is the spin. So once you can measure the spin property very precisely, we can extract the information of this particular energy difference. And using that, you can stabilize a macroscopic oscillator. So that's the basic idea of spectroscopy, and how you extract the atomic signal. Yeah. And similar to hydrogen, there are single electron valence shell of most of the atoms, the alkali metals. They all have single electron in the valence shell. That means, rubidium, cesium, sodium. That is why they are pretty active. It can undergo violent reactions as well because of that free electron in the outermost shell, which means you can say that rubidium or cesium are hydrogen like atoms. That means it has the lone electron with which you can again measure the spin state. So that's the basic idea. Now, how you hold these atoms in a small region of space, and what sort of interactions that you do in order to be able to extract the atomic signal, that's where the physics meets engineering. It's easier said than done, but that's where the challenge and fascination is in this work.
On your last note, you said where engineering meets physics. So you explained what the basic principle is behind an atomic clock, but how does it actually come into practice? Like how do they build atomic clocks using these scientific principles using
Yeah.
engineering?
So that's a great question. We said that there is this spin property, right? Now, first, let me give a small distinction that there are different kinds of atomic clocks. There are microwave standards, there are optical clocks, and then there are ion clocks, right? In optical clocks, there could be the lattice clocks or ion clocks. Now, let's take the simplest of the atom, that is hydrogen, or an equivalent alkali metal, that is rubidium. Okay, that's what I work on mostly. So let's take rubidium for example. The transition energy between the two ground states of a rubidium atom, that's 6.8 gigahertz, the oscillation between the two. We mentioned initially there is oscillation in these atoms, right? So now when we say that there is oscillation between the two spin states, which is 6.8 gigahertz, what it means is that the spin up and spin down can swiftly change between these two states about 6.8 billion times in 1 second. Okay, that is why we say it is 6.8 gigahertz. And what changes is basically is the spin up and down, right? Now, when you have these sort of rubidium atoms, which is basically a metal. So we can put these rubidium atoms in a glass cell, right? So if we have a glass enclosure in which you have put a small chunk of metal of rubidium, and if you heat this particular cell, then you can have a certain vapor pressure in the gaseous state. And that's when you know that you have certain amount of rubidium atoms corresponding to that temperature in order to interact. Okay, so that's how you confine the atoms in a small region of space in a glass cell. This is the first part, right? Now, the idea between the two ground states, let's say you have set this cell at a particular temperature. If we have, let's say, 1,000 atoms, okay, out of 1,000, 500 will have spin up and 500 will have spin down. So that means you cannot make an atomic clock out of this in thermal equilibrium. Therefore, we use light, or let's say laser, in order to pump the atoms from one of the ground state to the excited state. When these atoms are pumped from one of the ground state to the excited state, it will not remain there for a longer time. In about 27 to 30 nanoseconds, it will relax back. It has the probability to relax back to either of the ground state with equal probability of 50-50. If it comes back to the lower ground state, let's say, then it will be pumped back again. So this is called optical pumping. Once we do this in few milliseconds, we are able to generate a coherence, or a population inversion and coherence. That means all 1,000 atoms will have a particular spin state, and they're all now aligned in only one of the ground state. Okay, so once you do this, the corresponding energy difference is 6.8 gigahertz, right? We can generate the 6.8 gigahertz using 10 megahertz oscillator. That's where it all kind of starts from. You have a quartz oscillator at 10 megahertz. Then you multiply this 10 megahertz all the way up to 6.8 gigahertz using electronics, essentially. And the cell is confined inside a cavity, which means if you put a certain power of 6.8 gigahertz, this cavity is now oscillating at the same frequency. That means 6.8 gigahertz. In other words, the energy level difference between these two ground states, you can couple that 6.8 gigahertz to these two energy level states. Depending upon how much of power of microwave is absorbed, you know what is the change in the microwave power, right? So these are all physical quantities that one can measure: the light intensity, the microwave power, and the oscillation frequency. That means you start from 10 megahertz and then you step up and multiply. Now, by measuring these very minute changes, we can extract the atomic signal, right? Once you extract the atomic signal, then you discipline the macroscopic oscillator, which is 10 megahertz quartz oscillator. Let me give you a simple example here. If we take our wristwatches, okay, there are quartz oscillators in this wristwatch. That means if you put bias a certain voltage, then this quartz oscillator would oscillate at a set frequency. But the problem is the set frequency, which is around 33 kilohertz. That's the kind of frequency in which these quartz oscillators would oscillate in the wristwatch. It cannot remain at the same frequency all the time, whereas the atomic energy levels are fixed. If you are extracting a signal from the atomic energy levels, then you will be able to discipline the quartz oscillator. If there is any deviation in the frequency in the quartz, because the atomic energy levels are pretty stable, using that information, you can discipline the macroscopic oscillator. And then if you look at how stable your 10 megahertz output from the macroscopic oscillator is, that will be much more, much better compared to just a free running oscillator. So, the key challenges, if I want to summarize this, is how do you hold the atoms in a given region of space? And that is confine this metallic blob inside a glass cell. Okay, that's the first step. Then put this glass cell inside a cavity which can resonate at 6.8 gigahertz. Okay. Then you use some light source, laser, or there are lamps as well. Now let's assume that it is laser. Then you can pump the atoms from one of the ground state to the excited state, thereby creating that population inversion, bringing all the spin states to spin up. And then take the 10 megahertz oscillator, the quartz oscillator, multiply the frequency to 6.8 gigahertz. How much of that 6.8 gigahertz is absorbed by these spin states? This is very little. Huh? That means I'm talking of like zero point 0.5 or 1% of signal over 100% of noise, right? That's how tiny the atomic signals are. So, in other words, we can say we work with noise more than the signals in atomic clocks, right? So, the idea, therefore, is to discipline this macroscopic oscillator using the stable information from the spin state of the atoms. Does that make sense?
It does, sir. Just as a follow-up question, I want to ask. You said that we want to stabilize the microscopic oscillator using the stable frequencies of the atom. So these atoms, the transition frequencies are very precise. They are like the quantum of energy. The transition frequencies are always a constant, I suppose, and you use that as a feedback loop to give the microscopic oscillator every time the same frequency input. So I just wanted to ask: do we always need to run the atomic clock in a regular interval so that it stabilizes, or once we know that constant transition frequency value we can use that as a number to directly give it as a feedback loop? So why do we have to run it on a regular interval? Does that atomic transition frequency also has some variation over time a little bit?
Not a variation over time, but yes, it does get affected due to the external perturbations, which means, you know, how isolated can you keep them? That's where the difficulty is, right? If there are any variations of the magnetic field externally, that is going to impact these atoms. If there are temperature changes, that is going to impact these atoms, right? Now, the continuous operation is not really to stabilize the atoms per se. Okay. The continuous operation is because the quartz oscillator itself would start to drift pretty strongly. That means the frequency won't remain always the same due to the temperature changes, the pressure changes. This frequency keep on drifting and it will change. So therefore, the continuous operation is to ensure that the frequency of the quartz oscillator would remain the same. But having said this, the atoms themselves would also get affected. The energy levels would not stay exactly same, although on paper, you have exactly the same energy levels. They can get perturbed as well with the magnetic changes, temperature changes, the pressure changes, and the interacting fields. That means I mentioned the light in order to do something called as optical pumping. Okay. And I mentioned the microwave frequency. If there is any power fluctuation in the microwave frequency, that can again affect the energy level difference. And the fact that you have the light on in order to do the optical pumping, that can also shift the energy levels, which is something called as the light shift or AC Stark shift. Okay. So In quantum mechanics, the measurement itself would create the shift. So, therefore, these are all very sensitive and precise measurements. We need to take into consideration all these perturbing factors in order to eventually see what sort of stability that we can achieve with such clocks.
Right, sir. So now going on to a little bit of a bit on the societal impact of this timekeeping kind of concept. So these atomic clocks, as you have pointed out, and generally every science community knows, these are a really precise kind of clocks. Does a common person would ever require such a precision in his day-to-day activity? And why would such governments, as a whole, policymakers would want to invest in it, and why should they invest in it? What would be the driving aspects that would make them to push this technology forward?
Yeah, fantastic question. Um, you see, this is a question that I ask most of the people. That is, do you use atomic clock? Okay. More often than not, the answer is no, right? But let me tell you this: since 1967, everybody, whomsoever is looking at the time, are indirectly dependent on atomic clocks. Because since 1967, the definition of time itself is based on the cesium oscillations, right? Now, having said this, there is no direct impact on people's lives. Let's take few other examples which we are totally dependent upon these days. The GPS, or GNSS as it is called, global navigation satellite systems, we are heavily dependent upon this. Think about all the everyday activities that people do, taking an Uber, going from point A to B. When you order things on Swiggy and Zomato, for example, he needs to know where he has to come in order to deliver your food, right? Now, that's one aspect. And the second thing is the power grid synchronization. If you're transmitting the power from one big city to the other city, due to the phasor changes between these two distant cities, you will have huge power losses unless you synchronize the timing. Okay, so therefore, there is a pretty good synchronization that is necessary, and this is done via GPS or satellite signals. Okay, so synchronization essentially means that you have the phase to be matching at far away distances. Okay, so that's what the synchronization means. Now, in other words, if you have a 10 megahertz signal at a certain point, and at a far distance also you have 10 megahertz, how close are these two 10 megahertz as a particular 10 megahertz wave, how well they are matching on top of each other? Is there any phase difference between them? Okay, so this is synchronization. Few other examples that you can think of: the surveying, and these days people are doing the earthquake monitoring, the weather reporting. Okay, so there are n number of applications that you can think of which is directly impacting everyday lives, and therefore billions of dollars is at stake. When imagine that you don't have the navigation capability for a day or two, how many activities are going to stop because of that, right?
I feel like entirety of e-commerce will come to standstill if that happens.
Absolutely.
I wanted to confirm when you mentioned synchronization and all. Definitely, if you have two clocks, you need to synchronize them. But in atomic clocks, even a small change in height, position, and everything will cause a lot of changes in it. So, how do you synchronize two clocks? Let's say one is on ground and one is on, like as says, GPS satellites. So, how do you synchronize those two atomic clocks in general?
So we account for those offsets. That means you will have to take one clock as a master clock, and the other one need to be then synchronized for any changes that undergoes. Okay, for example, if the clocks on ground are mostly people use active hydrogen masers. They are much more stable than the small rubidium clocks, which are on board the satellites. Now, these rubidium clocks, I did mention about the drift of the oscillator, right? But overall clock can also drift because of at certain time scale these perturbing factors would start playing role. And at that stage, say for example, you turned on the clock and you started looking at the stability of the clock starting from 1 second, 10 second, 100 seconds, 1000 and so on. The rubidium clock characteristic is such that over approximately a day they would start to drift. Okay, now compared to these rubidium clocks, because these hydrogen masers are more stable, even at a 1 day time scale, they would still remain good. Okay, so therefore, you use the output of the hydrogen maser, and then every 12 hours, for example, you send the correction signals in order to synchronize the onboard clocks. Okay, now when it comes to this synchronization, you should always think in this way: you need a better reference clock in order to synchronize not so good clock.
This makes sense when we can communicate very fast between two. Let's assume in future we are definitely planning to go to Mars or future in other satellites. If there's a atomic clock on that spaceship, now the time that's gonna take for it, the signal to come from that spaceship to Earth might be much longer than what we are anticipating. So how do we calibrate our clocks in that way? For example, right now wouldn't be that much delay, but if it is going very fast or very far, then it will be very tough to synchronize, and we would need synchronization there.
Yeah, absolutely. That's a great question. So, you know, that is called deep space navigation. Okay. Now, which means you're right. For example, we want to go to Mars at some point. Now, the signal that it takes from Mars to Earth, anywhere from 5 minutes to 20 minutes one way, depending upon the time of the year, how far the Earth is from Mars, and so on. Now, which means for about 20 minutes, in order to communicate exactly where you are, say for example, your friend is standing on Mars, and then he said, "Hey, I am here," right? For you to know, it takes that 15 minutes. And by the time you communicate back, 15 plus 15, half an hour, he might not be at the same place, right? If he's revolving around Mars, let's say. So, therefore, you need much more stable clocks. Then you know locally, okay, this is my time, and therefore my position is also very well known, okay? Because 1 nanosecond corresponds to 30 centimeters of error. So, therefore, you want these clocks to be as better as possible over much longer durations of times. And therefore, if you take clocks which are drifting, it's not a good choice for deep space navigation. Recently, JPL, NASA, they developed something called as deep space atomic clock. These are mercury ion clocks which would have little or almost zero drift, and therefore on long term you don't need to synchronize these clocks even if they're free running, because there is no associated drift. Just one way communication is good enough because the other person's position is very well known.
So basically, I just wanted to ask why, if the mercury ion atomic clock doesn't have a drift, what is the difficulty of using it on ground applications? Is there some limitation to using it on our applications other than deep space navigation?
There's no limitation as such, but the technology development took many years. You know, it was only in 2019 such a clock was possible, right? So when it comes to space, we need to understand certain key aspects, and that is swap. It's called in short: size, weight, and power. Okay. Yes, cost is also important if you need to distribute to people, but when it comes to space, you outweigh these parameters, as opposed to cost. So size, weight, and power, which means there were mercury ion clocks which were kind of bulky, like a big refrigerator, right? So you won't be able to send that all the way to space. Point number one. Number two, the reliability of sending any product to space, because you won't be able to send somebody to repair if something goes wrong. You need to be absolutely sure that that is going to work continuously, tirelessly, for many, many years. Okay. That's when your mission is successful. So, therefore, to have a reliable operation of the clock and to reduce the size of the clock, but at the same time, not so much compromising on high performance frequencies. I mean, high performance of the frequency stability, right? So, all this technology development took that much of time, right? But now people are thinking that perhaps, the better clocks would be the ones which, like mercury ion clocks. Now, should we be doing next generation of navigation using mercury ion clocks? Okay. For instance, NASA is now coming up with Artemis mission. That means mission to moon. So there you would start developing new and newer and better technologies in order to do navigation. So therefore, such clocks will be very much useful. Sequence of it.
This was the first of the two parts of our episode of Zeroing In with Professor Thejesh Bandi. Zeroing In aims at bridging the pronounced gap between young enthusiasts of science, technology, and research and academicians and scientists throughout the Indian subcontinent and even further. Tune in to the second part of this conversation where we discuss further with Professor Bandi about the wider horizons of the field, perspectives on realizing a fully functional atomic clock from scratch, and further anecdotes from his experience.